I will talk about Interconnect. My name is Michael Kagan. I am CTO and one of the co-founders of Mellanox. Previous to my job at Mellanox, I was working at Intel with Ofri. Ofri was part of our team, and since '99 I'm with Mellanox. So what we are actually doing, we are doing the Interconnect. We're providing Interconnect solution for the computing and the storage. We started in the high-performance computing space. Now we are going to the enterprise. However, high-performance computing is one of the key things that we are focusing, and we are a leading interconnect provider there, and we intend to stand this way. Our core and initial products are chips, silicon chips. We also provide adapter cards. We provide systems of the switches and various gateways. The most tricky part is the software. So once we have all this hardware in place, we need software both on the host side application and on the network side to make it work. And last but not least, the cables. We are talking about very high signaling rate. We are talking about very fast data transfers. And we basically provide end-to-end solution, not only from the software, but also from the hardware perspective. We manufacture and sell cables to make sure that once you get all this stuff together, it's actually up and running. Well, this is just a few words about Mellanox as a company. We are a public company. We have about 900 people worldwide. Recently, we acquired another company, Voltaire, and now we have a full system solution end-to-end. And so what we are actually doing, Ofri talked about the CPU, and we do rely on our friends from CPU companies to make sure that the ALU is working right. Storage and application services is another thing, and what is in the middle is the network. And this is actually the brain of the today's data center. And if you look at what key data center challenges today and key challenges to build highly scalable, high-performance machine, be it a single supercomputer or big data center. By the way, if you ask Google what they are doing, they say we just built one huge supercomputer. So the key thing is to connect it efficiently and manage the delivery of the services efficiently, and that's where we are. So we are starting with the very low basic thing like high-speed interconnect. On top of that, we build capability to enable for this interconnect and these solutions to scale out. On top of that, we provide much more efficient and much more scalable interfaces to the applications, so each application can actually get the services either local or over the network transparently to the application. And last but not least, we provide integrated view of the entire cluster or entire network or entire data center to be able to manage it, to be able to handle faults if happens, and to be able to integrate this management with other services provided by our partners and companies. So this is some statement or some position of what InfiniBand is in the high-performance computing. Top 500 is the list of the fastest computers in the world, publish it twice a year. And what you see here is that more than half of the fastest computers, 100 fastest computers are built on InfiniBand technologies, and so on and so forth. We have entered this list in 2003 when our friend, professor from Virginia Tech, his first name is Srinidhi, his last name I can't. It will take about half an hour just to tell this name, it's very long. It's ex-jet fighter from Indian Air Forces. He just decided to build supercomputer, so he gone to the Toys R Us, more or less, bought about 1,000 Apple machines with the fastest CPU that were available out there, hooked it up with our wires and ended up to be number 3 supercomputer on the top 500 list in 2003. And since then, we are growing rapidly, and now InfiniBand Interconnect is about InfiniBand connects about half of the fastest machines in the world. Now, why? This is why. If you look at this slide, what it shows is the efficiency as measured by the top 500 organization. What they are doing, they are taking the benchmark they are running, and what amount of the floating point operations they get, and divided by the theoretical number of the flops you can get from the machine. So if Ofri talked about 50 cores, and each core runs at gigahertz, and each core has that many floating point units, so multiply it one by another, then add number of machines that you have of this, and that's the theoretical throughput that you can get, and the practical throughput is up there. And what you see here is that when you connect clusters or use InfiniBand as a cluster interconnect, you are ending up in the range of between 80 to 90, and actually there's one cluster that 96% of its theoretical floating point throughput. And there are some other red dots, which is proprietary Cray interconnect. And what you see, actually, the industry standard stuff that you can buy almost in price gets you the same efficiency as the proprietary interconnect designed by Cray. However, if you use some other interconnect like Ethernet, you end up wasting half of your money spent on the computing, because you get 50% on the utilization. GPU is another special thing that I'll talk about, and we do have some means of on our roadmap how to get this GPU faster. Well, this is the first. This is the 5 supercomputers that broke the petaflop performance. The first supercomputer ever that broke petaflop performance, it was about 2 years ago, I think. It was a Mellanox machine. Now there is a Mellanox connected machine. There is a few more, actually pretty much around the world. And this is the InfiniBand machines. What you see here from the technology perspective, it's about every 2.5 to 3 years, InfiniBand technology advanced one step further. Usually it is about roughly 2x performance improvement on the interconnect. Our first adapters were introduced in 2002, 10 gigabit, and recently we introduced 56 gigabit adapter of the FDR. And along the performance, there is also improvements in the scalability and overall efficiency and reliability. That part of this comes from software, part of this comes from the hardware, and part of this comes from the architecture evolution of InfiniBand. So FDR, F stays for 14, would you believe or not? So there's a 14 gigabit per second per lane data rate. Normally, you would run a link at the 4 lanes, so that's what gives you 56 gigabit per second data rate. It is obviously much faster bandwidth, lower latency, and much higher efficiency. It comes both from the encoding and the way the errors, link errors, are handled. So overall, you get not only theoretical but also a practical application visible efficiency. In 2011, we introduced 2 basic building blocks for the FDR, ConnectX-3 adapter and SwitchX device. ConnectX-3 adapter is the first, and I believe it's the only one so far, adapter that runs PCI Express Gen 3. There's a few server OEMs that qualified, along with Intel and us, the combination of PCI Express Gen 3, Sandy Bridge, and our adapter and their motherboard. So there's actually a few clusters on the last top 500 list were using FDR. SwitchX is the component that can switch 36 ports of 56 gigabit per second. It also supports Ethernet. By the way, ConnectX 3 also supports Ethernet, so basically you can use either up to 40 gigabit Ethernet or InfiniBand. SwitchX supports both Ethernet and InfiniBand networks, and it also integrates the bridges, so you can build all type of networks and network topologies using this SwitchX as the basic building block, and you can have connectivity between Ethernet and InfiniBand. This is latency and the bandwidth. If you see the blue lanes is the previous generation QDR, red lines sorry, the other way around. Blue lines is the FDR, and reddish lines is QDR. But you see the bandwidth is about 2x higher, the latency is about 2x lower, so basically you can access the memory on the remote node at less than 700 nanoseconds, or ballpark 700 nanoseconds, and it has a fairly dramatic impact of what you cannot do. It basically means that the access cost of local memory and the remote memory going down. And actually this translates, these basic capabilities or performance of latency and bandwidth translates to the benefit of the real application performance. In this case, it's molecular dynamics performance. So it's about 2x faster using more efficient network. So this is the InfiniBand cluster from Purdue University. It's number 187 on the, 54 on the top 500 list, but it got to almost 200 teraflops with 648 machines. 648 servers. There's a few more. LRZ is IBM and Leipzig Research Center. They're building a very large cluster with the FDR. They're planning to do like 9,000 nodes, 9,000 compute nodes cluster, and they believe they need FDR. That's what will give them the scalability and performance. Now, so we talked about the hardware and we talked about some basic things. Now, once you get this fast hardware, you need to complete the picture by having software to be able to support and take advantage of this hardware. So what we are doing, what's happening now is that the paradigm of the application development is that network is a bottleneck. And as a result, all the software starting from the low-level drivers and low-level protocols up basically was relying or considering this fact that application is the bottleneck, that the network is the bottleneck, and that's the way it was built. Now, once network becomes as efficient, or network efficiency or access over the network efficiency gets close to an efficiency of the local access, bottleneck moves up. So whatever used to be a network is not a bottleneck anymore. Now bottleneck comes to whoever thinks that network is a bottleneck and doesn't let the upper layer to use to access the remote node whenever it's needed, whenever it's good. And therefore we are working together with multiple software vendors and software companies, and especially in the high-performance computing space on the MPI, SHMEM, and PIGAS and the like, to basically update the libraries. And we have introduced the Mellanox messaging, MXM, that takes advantage of fast network. It is the very natural thing to use this huge floating points, scalable vector floating point machines to do the job of the high performance computing. And no wonder one of the classes in Japan, in university, they have multi GPU. They have, I think, 4 GPUs per compute node. So efficient usage of the GPU over the network is the thing that we have looked at, and we have this project and the technology, the GPUs that we call GPUDirect, that we developed together in NVIDIA about 2 years ago. And the first step is, and this is to make the communication or data transfer between the GPU computed data and and network to be more efficient. And this is the way GPU data is can be transferred. So GPU calculates the results and it stores it in local memory. Then you copy this data to the system memory, to the GPU buffer. Then from GPU buffer you copy to the network buffer, and then from network buffer you send it over the network. And on the other side there's the same picture. So there's quite a lot of local data transfers within the node, which are pretty redundant. And if you look at this one, which is the copying data from GPU buffer to network buffer, or other way around on the receiver side, this is the most expensive and most troublesome one, because this is done by the CPU itself. The CPU, instead of doing the job, it copies the data, and these two arrows is just moving the data from the GPU memory to the system memory, just moving the data on the local node by the GPU DMA. So what we have done, we have enabled to share network buffer with the GPU buffer, and as a result, we ended up getting rid of this memory copy from the GPU buffer to network buffer, and vice versa. This is the first stage of the GPUDirect, and the performance gain you see by removing this copy, or eliminating this copy, is in the range of 30%, up to 32% on the real application. So the next step is to be able to present GPU not as a local hardware resource, but as a global service that is available and over the network and can be managed independently of the compute services. So think about the analogy that you have with the storage. Okay? Here you have a CPU and the GPU on every compute node, and the application that needs GPU services or can use GPU services has to run on the same compute node that happens to have this GPU. What you can do, you can actually take the GPU and put them on the different machine and tunnel the interface between the application and the GPU over the network. And if your network is fast enough, and that's yet another example that where local access and remote access, once they are close enough, you can basically do things very differently. If the network is fast enough, and you have the RDMA, so you don't bother CPU by accessing the memory, you can get performance of the remote GPU very close to the local GPU. So what you see here is this is the two most interesting bars. There is a matrix product benchmark. If you run it on the CPU only, you get 1.3 seconds. If you run it over the GPU, you do it about twice faster. And if you run it over a remote GPU, it's pretty much the same time. Now, if you do it with the wrong network, running over Ethernet and TCP, you actually get worse results than without GPU itself. So this technology enables you to segregate the GPU and the CPU, and you actually can present the GPU floating point, vector floating point, as a service. So the application that needs to get it can send the job there over the network instead of locally, execute it on the remote GPU and get the results back. Few words about the network. Network scalability starts at the very, very low level of network of hardware reliability. If you have a network error like bit flip, then you need to retransmit. If your bit error rate is low, which is 10 to the minus 12 or 10 to the minus 15, then on the cluster of 1,000 nodes, this retransmission happens very infrequently, like once a day. Not a big deal. But if your cluster is 100,000 nodes, then this retransmission can happen like every second. So improving the link reliability is sort of the first step to make sure that stuff works and performs at scale. The next thing is to make sure the data that you are getting over the network is not being corrupted by the means that is not detected inside. It can be corrupted inside the devices. So therefore, you have InfiniBand technology has end-to-end transport level protection. It is similar to TCP checksum. It is more powerful than TCP checksum because it's a CRC, and it's actually two-level CRCs. One is for link layer and one for the transport layer. So you can stay assured that the data that was sent from one place to another place is not getting, yes?
What fraction of the bandwidth is used for forward error correction?
0. 64, 66 bit encoding, that's it. I mean, 0 compared to anything else.
That's the forward error correction?
Yeah. Forward error correction is it doesn't really use the bandwidth. Okay, what it costs you a store and forward latency of 1,000 bits per lane to calculate to fix the error if it happens, and it's being detected by the encoding. Okay, this is the fact. It's okay. Okay. So this is the forward. Now there's a additional forward error correction, which is you can deploy. This may cost you additional bandwidth, but it's negligible. It's in the range of I don't know, 2%, 3%. The 64, 66 bit encoding error correction gives you a link reliability of order of magnitude of the 10 to the minus 15 to 10 to the minus 17 bit error rate. The extended error correction gets to reliability about 10 to the minus 100, which practically means there is no uncorrected error. And this one costs about 3% bandwidth. Now, on top of that, when you send the data from one station to another, you want to make sure that, and when data also rests in memory, you want to make sure the data was not corrupted and was not something bad didn't happen at the data structure level. And in Mellanox adapters will provide ability to do the application level signature protection, which is above and beyond. It's actually not related to the network signatures, be it transport level or link layer. Basically, you can, when you store your data structure, you can calculate some CRC or checksum. And when you read this data structure back, our hardware supports line rate of calculating and validating this signature. And if the signature is wrong, you know that your data was corrupted either on the way or in the local storage. Network topologies. Today, most of the clusters are built using close or factory network topology, so there is a full bisectional bandwidth all the way across the network. It is cool if you want to run one application on the entire cluster. If you want to, if your application doesn't really have equal communication across the nodes, or you can have multiple applications, you want to allocate your machines differently. There is different topologies being deployed and developed, mesh, 3D torus, butterfly, and so on and so forth. We support today in our software of the network management 3D torus and factory, and we have a more wider range of topologies to be supported in the coming software releases. So if you look at the way a network is managed, it is managed in some sort of, there is one guy that is called subnet manager that overlooks the entire network, and it sets the network routing as a default, static routing, that's what were used in all the networks. Adaptive routing is enabling the offloading, I would say, from the subnet manager to the network, some low-level decisions of how actually to forward the data, not necessarily on the strict routes that are set. And network that is lossless, it has to have a congestion control in order to perform right. And in addition to that, if your higher-level management, and we'll talk about it in a few slides, is aware about what's going on, you can actually do the routing in a way that is optimized for the applications or set of applications that are running currently on the cluster. So first thing is the network congestion. What you see here, the example what you see here is that you have multiple sources targeting the same destination, and no matter what you do here, if there's a 6 guys trying to send data to one, and sometimes it happens, especially dynamically, each one will get 1/6 of the bandwidth. But the problem is that whoever is on the way is also going to suffer, because if you look at this switch is going to divide the bandwidth between of this single drain between multiple inputs more or less equally, and therefore the paths that are going over here and this link it will be heavily underutilized. So the way to handle it is to tell these guys, don't send the data at the full rate. You're not going to get it to the destination at full rate anyway. And this is called congestion notification. Switches determine the congestion and send notification back to the notification being sent back to the sources, and sources throttle down the injection rate. Now with the network speed that we are talking about, 56 gigabit and soon 100 gigabit, this is not something that you can do in the software like TCP throttles the congestion today on the internet. It has to be in hardware both congestion detection, and you need to do it not by dropping the packet, so transport layer will know that you need to slow down, but by figuring out that your queue is being built up and sending the notification back to the source of this data that's being sent, and this guy needs to install the rate limiter and throttle down the injection rate, and all this loop needs to be closed in a time that buffers will not blow up. Now if you look at the network buffers, in the InfiniBand, network buffers are measured in kilobytes, sometimes tens of kilobytes, maybe 100 kilobyte. If you look at there's a good reason to have shallow buffers, because if you have a deep buffer, it inherent latency error, and this is what enables you to build very high density, high port density switches and run them at high performance. So this is the real example of congestion control. This is the example where you have multiple nodes congested, and when congestion happens, what you see here is that network actually loses the throughput. The congestion causes the dramatic loss of performance. When you turn the congestion control in, you see basically network is being used at the line rate. So whoever can send the data at the full rate sends the data at full rate. Whoever cannot doesn't do it, but they don't pollute the network with the data that cannot be delivered to destination. This is congestion control as measured by benefit of congestion control as measured by at low level benchmarks, and also on the application. In some applications you see it's almost 2x performance benefit. So the congestion, you need to slow down the injection rate when you have a true congestion. True congestion means that there is a multiple sources sending data to single destination. However, due to static routing, you may have a false congestion. So here, what you see here, that everybody sends data only to the one destination, but due to the routing, you end up with the hotspots within the network. So the way what you would ideally want to do, if you see this case, you would like to change the routing. So the routing will be done in a way that that hotspots are disseminated across the links. Unfortunately, not these congestions may happen at for the very short time. So you don't really have time by the subnet manager in software to go off and reconfigure all the switches. So what we have here what we call adaptive routing. Basically, in this case, each switch is programmed to have multiple choices of how to forward the data, and it makes the decision based on the load on the network. And this is long table, but lot of words here. But simply said that when you have the fault congestions, you can get in this example about 2/3 of the network performance. When you turn on the adaptive routing, you basically recover pretty much entire performance loss due to the false congestions. Yeah.
You change the route in the middle of the stream of the flow.
You change the route when it's appropriate. You change the route when it's appropriate.
And you manage the out of order because you change it.
Okay, so there's a multiple ways to handle this problem. One of this is to change the route considering the flows. This way or another. The other way is to how do you handle the out of order on the endpoint. You can tackle this problem in the multiple ways, and that's what we are doing. Okay. Unified Fabric Manager is the software package that we provide to our customers that enables a single view, and actually more abstract view than the real hardware over the network. So you can, well, I'm running out of time, automate and monitor your machines. And when we talked about the network topologies and with this virtual network topologies, basically Unified Fabric Manager can configure the network according to the logical topologies that user wants to see, and it can present network in the multiple layers. So basically, and one of the things our friends from Platform Computing are doing, they're using this to do the smart job scheduling to get the things to utilize the cluster and to give the best utilization of both network and the software and the servers. So, in summary, we provide the solutions for the network connectivity, for the data center connectivity. It can be used for the Exascale high performance computing. It can be used in the enterprise data center. We have the scalable offloads, we have collective offloads, and we have the basic interconnect. That's what we are doing for the high performance community. But I don't want to leave the stage before I have a few words about the enterprise. And the enterprise today, which is Web 2.0 or cloud, they actually use the high performance computing technology to run their applications. If you look at companies like Microsoft, Google, Yahoo, Amazon, some of them are using all their data centers just to run a single application. Some of them are using their data center to provide computing services to different people. That's the difference between Web 2.0 and cloud. And if whoever uses Bing Maps, if you run Bing Maps, all the stuff runs over Mellanox wires. Bing Maps data center is built based on the Mellanox InfiniBand technology. So, what core of the technology is to be able to expose or offer multiple I/O channels and manage quality of service, which is isolation and memory protection in the hardware. So it means that now you can have a pretty much infinite number of I/O channels, and you can expose each I/O channel to different applications directly, and you can to untrusted entity. So like you can run natively on the hardware of the adapter, same way as the application runs natively on the CPU core. Example of this is using the virtual machines. That is the part of the, or one of the key parts of the cloud. You can actually have a virtual machine getting the I/O services directly from the network at the same speed as it would have been a physical machine. And this enables you to deliver cloud services, cloud computing through the virtual machine technologies in the same way and the same efficiency as it would have been native hardware. Another thing in the Hadoop and Memcache, there's two big mid layers or applications that are using in the Web 2.0 and cloud. Hadoop is the heart of the search engine. By using faster network, what you can see here is that actually if you use faster advanced network, you can scale by getting the faster network. If you use TCP, it does really matter the performance of the 1 gig versus 10 gig. But if you use RDMA, then by getting faster network, you can actually get a better performance. This is example of using more advanced network technology with the Memcached. Memcached is basically the database cache that is used heavily by people that are providing the interactive web services. It is, Facebook, Google, all these guys. And this is the performance of the raw I/O performance. Basically, what you see here is that a little bit busy slide, but you see here that the virtual machine gets the I/O performance of the native physical machine by using ConnectX adapter. That's it.